Can I jump in for questions?
Yeah, please,
Yeah.
everyone.
Yeah, it is a very nice talk. So, one of the things is that you are neglecting the effect of. So you are considering rotation, but you are not using the rotation effects on the dispersion relation. So you are not considering something like, say, Poincare waves, and also you are ignoring the effect of the geostrophic current. But you are keeping rotation just in one place. I mean, and the other thing is, you have said that your wavelength can be in the order of kilometers, and you are using deep water limit, but the ocean at times the depth is around the order of kilometers. So how is the deep water limit also justified? So these are my first two questions, if you could.
Thanks for these questions. Yeah, very interesting questions. Firstly, so the effect of rotation, we just took it to be in a vertical direction as a first approximation, and I forgot the very first question. Sorry.
So it was like you are taking the effect of rotation. Yeah, that's but you are not including the geostrophic current that is induced by the rotation. That's one kind of a mean flow you are ignoring, and the other thing is that you are also ignoring the effect of rotation in the dispersion relation, which I think is fine. Because
So dispersion relation, that comes actually at a higher order. So you can do do the expansion, and where is that expansion? Yeah, if you do this expansion, you do have a correction higher order, which again comes, and if you write just the velocity field for the wave, you do have a correction from the rotation on the dispersion relation, which comes at a higher order. So at this particular, if you truncate it at this order and say we are only interested in this, we do not consider that particular effect. But in reality, I think we still are quite good, because there's still quite a large scale separation, even for the 1 kilometer long waves. I still think
for 1 kilometer long wave it is fine. But can you for 1 kilometer long wave use the deep water limit?
That is a very interesting question. Actually, if you look at the article by Longe-Higgins, he does say that there's a bottom boundary layer which starts to develop whenever you have a wave which is propagating on a not so deep water limit. So obviously, we do expect that the mean flow that is being driven, because the mean flow which is driven in this system there's a boundary effect, which is what we showed here. There's an upper boundary effect because because of the no stress boundary condition. Similarly, at the bottom, because it's a no slip boundary condition, you do have a strong boundary layer which will be developed, and this again would play a very important role. And the question is, will it be a laminar dissipation or will it be a turbulent dissipation? That we don't know yet. So these are interesting questions that one should look at. We didn't think about such extensions. So we just took the simplest problem that we thought of, and then we analyzed it. But these are the directions that one could potentially think about. And with respect to your geostrophic current, if you have a strong geostrophic current, it is known that you will have these Langley circulations that get formed. And the question is, so this part is very well studied, like the effect of the background current along with the waves and the formation of these Langley cells. Even in a rotating frame, I think people have studied it, but I don't know how much study which I did currently would be related to, because I'm getting an instability which is in the direction which is transverse. So I don't know how this instability will interact with the Langley cells. Will it kind of create a direction component to it? So these are again questions in the long run which we have to think about. But for the moment, we just stuck with the simplest setup.
Thanks a lot.
Okay, some other questions, please.
Hello, Kanna. This is Raja. Hello.
Hello. Yeah, can you hear me? How are you?
I'm doing good. I just have a small query because I somehow lost at some location. You said somewhere like waves transmit their momentum to the main flow via surface stresses. Can you explain me from the picture, because I had a difficulty in terms of visualizing that.
So okay. So I have one particular way of explaining it, which many people might not be very happy with. So let's say if you have a system which is like you have a mean flow and you have waves that are propagating on top of it. So the waves kind of just the waves without, let's not worry about rotating and stuff, just waves which are propagating on top of a stationary fluid, because the waves actually kind of move from one direction to another direction. There is some kind of, if it considers some viscous effects, you have some kind of shearing that is occurring at the topmost layer. So the waves are shearing the bottom fluid because they're moving from one particular place to another particular place. So you have an effect of waves which are moving in a viscous fluid. Since you're like pushing waves from one direction to another direction, these waves are trying to transport its momentum from one place to another place, and while transporting this momentum, it loses some momentum due to some shearing effects because the bottom liquid is actually stationary. So it kind of loses some momentum in the process, and this loss of momentum can be thought of this surface stress. Another way, like more crude way, would be like, yeah, you are like kind of pulling some kind of a sheet on top of a system of a tank of liquid, which, I mean, not exactly the same thing, but I don't know. I kind of like that particular analogy. If you kind of pull it, you have some kind of a sheet which is being pulled, and that kind of transmits some momentum to the underlying flow. And the sheet, you can think of it as some wavy sheet. But yeah, it's not the same problem, but it's another way of thinking about it. I don't know if that makes.
So is it approximately the very crude approximation Newton's third law?
Is it a crude approximation of Newton's third law? I mean, there was some.
Now, what you're saying is like third law, no? When somebody's going ahead, then he'll push it.
Yeah, it kind of seems like that, but I don't know whether I should make that link. I don't know.
Anyway, so that's my stupid remark, but
yeah, no, I don't know. Maybe there's a profound meaning to it, and I'm not seeing it. So I'm like, I don't want to I don't want to say whether it's yes or.
Okay, Abhishek, please go ahead.
Yeah. So hi, Ghana. Can you hear me?
Yeah, I can hear you. Yeah.
So very nice talk. Can you go to the slide where you showed this scaling? So this Lagrangian velocity has a Ekman 1/3 scaling, and the other one, the mean flow, has a constant. So I was trying to understand that, get a physical picture. So so the particles follow the Lagrangian velocity. So does it mean that changing the viscosity changes the way the particles move, but it doesn't affect the way the mean flow moves, especially if you go to lower and lower Ekman numbers? Is that how we should read it, or?
Good question. So changing the viscosity would be like equivalent to getting let's say if you keep reducing the viscosity, what you end up is an Eulerian velocity field which becomes closer and closer to the anti-Stokes flow. And basically, it's the difference between these two, the Stokes drift. So you have one component which is the Stokes drift. It's the process in which the waves kind of pull particles along with them. So you have particles which are moving along with the waves. But you also have, because of the rotation, you also have an effect in the opposite direction, which is the anti-Stokes flow. And the Lagrangian velocity is actually a difference between these two competing processes. So in a sense, if you interpret it in terms of reducing viscosity, you do see that in one case the transport property seems to be affected a lot, though the velocity field themselves, the UM component at least, seems to be more or less constant, right? Like it's about of the order 1.
So it becomes independent of the viscosity.
It becomes independent of the viscosity, but the transport property, because it's a competition between these two competing effects, it does seems to be very very sensitive to the exact value of viscosity. Yeah.
Okay.
Okay.
So shall we go to the next question? David, please go ahead.
Yes, thanks. I wonder if I could just ask about, you had an equation for the mean flow, and you leapt from the time evolution equation to the steady state, kind of.
Yeah, I think from here to, I just jumped here.
Yeah, that one for it. Oops, the other one, the one that's a DT UM. So, but presumably there's a question about whether it does evolve to the steady state, or indeed the time scale. I mean, if the rotation is so feeble, then presumably it's going to take forever to get there or something. I mean, I can see that there might be a steady state, but I could also see that from your evolution equation for the mean flow, it might take forever to get there, or it might not get there actually.
Yeah, that's a very good point. And yeah, we did wonder about that, and we could only answer that after we did the nonlinear simulations, right? Because just by looking at this equation, we are not whether, because there are multiple time scales. You have one time scale which is a rotation rate. You have one viscous time scale. You have this advection time scale by this Stokes drift. So we do not know along which of the time scale it evolves into. And it's a very good question whether does it actually lead to the mean flow. So what we did was that when we did the simulations, nonlinear simulations, we got strong effects of this quasi-inertial waves. So you have these quasi-inertial waves which are existing always, and on top of it, you do have a mean flow which gets generated, and this gets generated over the advective timescale. It doesn't take the rotation timescale to get established. It gets established in the advective timescale. Whereas the rotating timescale controls these quasi-inertial waves. So if you look at the time series, you have something which is oscillating at the frequency of you have some oscillations at the frequency of f, which is a very slow process. But on top of it, you do have a generation of a mean flow at that advective time scale. And on top of it, you have instabilities that occur much. So for example, if you look at this particular plot, for example, here I show some two different values of Rossby. I mean, it's a particular type of box which I took. So the exact values depend on the geometry of the system. So here it was not a very good choice of the box. So you just have to excuse me for this weird values of Rossby. But if you take this particular time scale, so you have an instability that goes at an advective time scale, right? So you have a mean flow that gets established much faster, and you have an instability that goes on top of a mean flow, and this gets established of the order at the advective time scale. So even though you have a time scale which is like much slower, which is the rotation rate of the Earth, you do have instabilities that go much faster, and this rotation rate mostly governs the quasi-inertial wave part of it. And if you look at a velocity field, you have a strong component of this quasi-inertial wave, and you have an instability properties on top of this quasi-inertial waves. I hope that answers your question. Was it clear?
Yeah, I think so. Yeah, that's good. Thank you.
Thank you.
I have a quick question for you. So high Rossby number basically means almost no rotation, right?
Yeah.
I mean, that's also so in your case that when you have a very high Rossby number, you have an exponent. You show a very high exponential growth and reasonably good exponential growth. So the mean flow is growing, and so what happens to the surface waves because of this growth? Do you see expect the surface waves to grow exponentially too?
Yeah, I mean that is again another interesting question. So unfortunately, we did not study the reaction of this mean flow on top of on the surface waves. So for that, we have to write a nonlinear Schrodinger equation to understand the effect of the mean flow on top of the surface gravity waves. So according to this expansion that we did, the asymptotic expansion, we just said that the amplitude of the mean flow is too weak to modify the waves. So if you say that the amplitude is AK of the wave, the reaction would come of the order of AK cube. So because the reaction is of order of AK smaller than the linear term or the interaction term between the waves themselves, we kind of remove that heteroaction term. But it's an interesting question whether the high rate of change would it actually modify it. This again, one has to write the nonlinear Schrodinger equation, write down a coupled set of equation that kind of respects all the symmetries and conservation laws, which we were supposed to do, but we didn't do because this only took quite some time for us to understand.
Yeah. Okay. Thanks a lot for your.
Thanks. Yeah.
Okay. So I guess there's no further question. Anyone else? Okay, so formally we can close the. Yeah, Sonakshi, you have a question?
Yeah, so based on what the previous question, so you can have rogue waves coming out of this system, right?
I mean, if the effect, yeah, I mean it's something to think about, but I don't know whether the mean flow would be so strong to affect the system to give rogue waves. I mean, my understanding, I mean, I have like not much understanding of the literature along the low wave direction. So my understanding of rogue waves is that you have you have a better chance of getting rogue waves when you have linear waves which are like not not aligned along different in the same direction. So when they interact at certain locations, we get this large amplification. But I do not expect the mean flow to change the phases of these waves so much that you can get rogue waves. But maybe there's a localization occurring. It's an interesting question because there's a spatial structure. There's a localization which might occur, but I do not expect it to amplify the waves by a lot of factor though. There might be some localization, but I don't expect rogue waves to come out. As in, I don't expect the wave.
But when you couple it with the nonlinear Schrodinger equation?
Yeah, that is what I'm saying. Yeah, when I couple it with the nonlinear Schrodinger equation and write the evolution equation for the envelope, I do expect some spatial dependence to occur, and I do expect that at certain locations you might have a wave which is slightly higher amplitude than at other locations. But because the coupling itself has an AK square parameter, which is smaller,
and that is low in
it is a very smaller parameter. So I do not. I mean, it's an interesting question, but I don't think. There might be some localization, but I don't think it'd be like large enough to create to create a rogue wave, like the technical definition of a rogue wave. Yeah.
Okay. So I think we can formally close the seminar, but people can stay for chat if you like.